In this video, we will see two examples of systems with variable mass. As the first example, we will discuss the mechanics of the conveyor belt. We know that in most of the industries, conveyor belt is used to carry goods from one part of the factory to the other on the assembly line. So typically a conveyor belt is of the form of a belt which is rotating on a platform mounted on wheels, and the main feature of a conveyor belt is it moves ahead with a constant velocity v. Suppose capital M is the mass of the conveyor belt, and suppose there is a stationary hopper placed. So hopper puts some mass at a fixed location. Let us say that this mass is put on the conveyor belt at a constant rate given as dm by dt. So it has units of some kg per second. So let us say this rate is suppose 0.1 kg per second or 0.3 kg per second and so on. So on this conveyor belt, this hopper which is stationary puts some amount of mass at regular intervals of time. So it has got a rate of increase of mass because this whatever amount of mass dm is put in an interval of time dt now becomes the part of this conveyor belt system. So let us say a mass small m is present on this conveyor belt at some instant of time t. So in that case, the total mass of this conveyor belt is going to be small m plus capital M, and the velocity is constant given by letter capital V. In that case, the linear momentum by definition is going to be m plus m, which is the total mass of the system, into v, which is the velocity of the system. And by Newton's second law, the force required would be equal to rate of change of momentum as a function of t. So this, if we expand, gives us mv plus mv. Out of these quantities, mass of the conveyor belt is fixed, so it is constant. Speed of the conveyor belt with which the blade is moving ahead, taking the mass small m, is constant. So the only quantity changing is small m, because this mass of the material is continuously added on the conveyor belt via the hopper. So when we differentiate these quantities, mv plus small mv, this entire thing is constant and hence its derivative is 0. This speed v is constant and we get a dm by dt. So the force acting on this conveyor belt system along with the mass of the material is equal to v into dm by dt. Call it as equation A. Now we will calculate the power required to keep this system moving. By definition, the power P is equal to force into velocity. So this is the definition of power. If we use equation A here, we get V into dm by dt. Remember that this velocity V is constant, so it can be adjusted anywhere inside this d by dt term. So we get it equal to d by dt of mv squared. So this can be further written as P equal to half of twice d by dt of half mv squared. So a 2 factor of 2 is adjusted both at the numerator and denominator. But by definition, we know that half mv squared is the kinetic energy of the system. So let us say k equal to half mv squared. So in this case of conveyor belt, we get the power equal to twice the rate of change of, so this is k, so twice the rate of change of kinetic energy. And this expression is a bit tricky because if we compare this with the ordinary case where the mass is not changing or the mass is constant, remember that in case of a conveyor belt, which is moving with velocity v, the mass m is continuously getting added to the system. So the mass of this system is not constant, but it is variable. So for this particular result, or for this particular case, we are getting this result. Now for an ordinary mass m, which is fixed, which is moving with velocity say v, we should get the power is equal to force into velocity as usual. Now if mass is constant, force is just mass into acceleration into v, and acceleration is dv by dt by definition. So this can be written as 1 by 2 m of twice dv by dt into v. Now this can also be written as 1 by 2 m d by dt of v squared, right? Why? Because derivative of v squared will be 2v dv by dt, which is what we are observing here. Again, we can write it as d by dt of half mv squared, since mass is constant in this case, and here half mv square is as usual the kinetic energy, so we get dk by dt is equal to p. Now if we compare this result with the case of conveyor belt, in case of conveyor belt, the power required for keeping the system moving was twice the case for constant mass system. This result is followed for constant mass system, and this result is followed for conveyor belt, which is a variable mass system. So the essence of this important observation was to show that whenever a system is of variable mass, it behaves slightly differently than the ordinary cases. Let us try to discuss another example, which is very famous one, of motion of a rocket. So let us label it as rocket motion. rocket motion. So we assume that there is a rocket which is having mass m and which is already moving with a speed v in upward direction. So throughout the discussion, the upward direction will be considered as positive and downward direction will be considered as negative. Let us say this is the values or parameters at some instant of time t. Now in case of rocket, we must remember that the rocket is a combination of two subsystems. One of them is the body of the rocket, and a significant fraction of mass is contributed by the fuel which burns and carries the rocket ahead. In order that the rocket travels much farther distances, we need to have a large amount of fuel present inside the rocket. So this makes the fuel to contribute a significant share to total mass of the rocket. And as the fuel burns, it is thrown out in the form of exhaust gas, which pushes the rocket in the opposite direction. But as a result, since this fuel burns out, the mass of this rocket goes on decreasing as it moves ahead. So it makes it this operation makes it a system with variable mass. Let us try to discuss the mechanics of this system. So we will consider this case where initially at some time t, the rocket has a mass v which is moving with velocity v in upward direction, which is considered as positive direction. At some later instant t plus dt, some of the part of the mass of this rocket, which is in the form of fuel, is burnt. Let us say that a small portion of mass delta m is burned and it is thrown in the downward opposite direction to the motion of the rocket with say a velocity u. As a result, the rocket gets a push so that its velocity is now increased by some small value delta v. And at the same time, its mass is decreased by a small value delta m. Now we can see what is happening with the momentum of the rocket. So let us try to find out the initial momentum. Call it as pi. By definition of momentum, we know that momentum is mass into velocity. So at instant of time t, pi is going to be just m into v. The final momentum at some later instant t plus delta t, let us make it as delta t, which is a finite interval of time, pf would be the momentum of rocket plus the momentum of the exhaust gases, which are the burnt fuel. So the momentum of the rocket is just mass into its velocity plus the momentum of the exhaust is its mass into its velocity. Now the force acting again by the Newton's second law of motion would be rate of change of momentum with respect to time, that is delta p by delta t. In this case it is going to be pf minus pi upon tf minus ti. Pf is simply equation 2 and pi is equation 1. So let us substitute those values. Now this equation 2 can be further simplified by multiplying these terms. So we get 4 terms and this one is the fifth term. So what we get is m into v plus m into delta v plus minus delta m into v minus delta m into delta v. So this everything is nothing but pf minus pi. Pi is going to be m into v divided by tf is the later instant of time t plus delta t minus ti is the previous instant of time which is called as t. Now remember that we are calculating the force here. So this is equal to, this mv gets cancelled, this delta m into delta v is too small, so it can be neglected as it tends to 0. So what remains is this, again the t gets cancelled, so we have with us m delta v by delta t minus v delta m by delta t just cross check that this term I forgot to include. So plus there is a fifth term which I had mentioned, that plus delta m into u, right? So this term will also be present here. So plus u into delta m by delta t. So f is going to be equal to, now we will take limits as delta t tends to 0. So after the limits are taken, this delta v by delta t becomes dv by dt and this delta m by delta t becomes dm by dt, and delta m by delta t, which has now become dm by dt, can be taken common, and inside the bracket we get u minus v. So this is the force acting on the rocket at any instant of time t. Now we will further substitute another quantity. This u minus v is the relative velocity of the exhaust, that is the velocity of exhaust with respect to the rocket. Call it as some v relative, which is the exhaust velocity, or the velocity with which the exhaust gases are moving with respect to the rocket. So if we make this substitution, the force experienced by the rocket would be m dv by dt plus v relative dm by dt. Let us say this equation to be equal to A. Now since this is the force, this is ought to be the external force acting on the rocket. Now we will consider the case where the rocket is moving under the effect of gravity. So in case of gravity, we know that F external is just m into g. So use this equation in the previous equation, we get mg equal to m dv by dt plus v relative dm by dt. Now we will try to include the directions. Gravity is acting downwards, so it is negative. The rocket is moving upwards, so it is positive. And the relative velocity is also in the downward direction, so it is negative. And the last quantity dm by dt is the rate of change of mass of the rocket as function of time. And we know that as the fuel is burned, the mass is going to decrease. So as t increases, m decreases. As a result of this, even this rate of change of mass is going to be negative. So if we apply these four conventions of directions in this equation, what we get is, for g we get a negative sign, so we write it as minus mg. For v we get a positive sign, so we keep it as it is. So plus for v relative we get a negative sign, but remember that even this quantity is negative, so negative into negative gives us a positive sign, so it is also kept as it is without any change. Now we can divide throughout by m to get g equal to or minus g equal to dv by dt plus v relative 1 by m dm by dt. This can be rearranged. If we multiply throughout by dt, we get minus g dt is equal to dv plus v relative 1 by m dm. So now we can integrate in between two instants, say t0, which is the initial time. In this case, t0 would be just t equal to 0, that is where the clock starts. Say v0 is the speed of the rocket at this initial instant, and v is its speed at some later instant t. So this equation can be integrated. Similarly, m0 would be the initial mass of the rocket, and m would be the mass of the rocket at some later instant t. So when this is integrated, g is a constant, so we get g integral dt between 0 to t is equal to integral dv between v0 to v plus v relative. We are assuming that v relative is constant, integral 1 by m dm from some m0 to m. Now this gives us minus gt is dt integrated gives us t, upper limit t minus lower limit 0 gives us t. When we integrate dv, we get v, so upper limit minus lower limit gives us v minus v0 plus v relative. Now here integration of 1 by m dm gives us log m, and upper limit minus lower limit gives us log of m minus log of m0. Now we can adjust this term a bit, because v minus v0 plus v relative, now this term has to be adjusted because m0 is the larger quantity than m, because m0 is the initial mass, and as the rocket moves ahead, its mass is going to decrease. So we'll rewrite it by taking negative sign common as log of m0 minus log m. And now we note that log a minus log b is log a upon b, so this is v minus v0 minus v relative log of m0 upon m. So again we can readjust to find out an expression for v, which is the speed of the rocket at any instant of time t. V equal to So the remaining two quantities can be shifted on the left hand side to get V equal to minus gt. We shall write V0 first, which is the initial velocity of the rocket, minus gt plus V relative log of m0 upon m. So this is an expression for speed of the rocket at any instant of time t under the action of gravity. If we consider the special case where gravity is absent, so rocket is moving in free space. So this happens when the rocket goes very far away from any planet, at least in principle. So when gravity is absent, this g is now 0. So v is just equal to v0 plus v relative log of m0 upon m. We can further see that if the rocket starts from rest, this v0 is then 0 in that case, which is the initial velocity of the rocket. So this formula gets further simplified as v equal to v relative log of m0 by m. So this is a much more simpler formula which is applicable only when the gravity effects are negligible and the rocket starts from rest. So this was regarding two critical curious examples of systems, how their mechanics is derived when their masses are variable and not constant. Thank you.